Okay, this is a review of Castle Unit 4. This would also help you with the internet homework that's due this weekend. So I wanted to consider two easy circuits here, finding the equivalent resistance like what's in the internet homework. I want to start easy because you know the answers for these, and I want to show you the importance of the color coding because I'm not sure everybody's getting how important it is. Some of the most important stuff we're learning right now. So if you're looking at this, you can see that this one's totally in series, right? We know that one on the left, and on the right, this one's in parallel. But before we just solve this without thinking, I want you to think about applying this idea of color coding, which represents the pressure. Let's say the left-hand side of each one of these circuits is connected to the positive terminal of the battery, and the right-hand side is connected to the negative terminal of the battery. So that means on the left-hand side is going to be high pressure, on the right-hand side is going to be low pressure, and so that's represented with red and blue respectively, sort of like this. Since these are two equal resistances on the left, in between the two resistors for the series would be yellow, exactly in between the two pressures of red and blue. And what I want you to get from this is that there's a pressure difference across the resistance. It takes a certain amount of pressure to drive that flow through that resistor. And if there wasn't a pressure difference, then there wouldn't be a flow. And so what I want you to see here is that whenever you have things that are in series, you're going to see a pressure difference through them. Whereas if they're in parallel, they're going to have the same pressure difference across them. Okay, so how are we going to apply that? Let's look at this more complicated situation. It's kind of hard. How do I figure out, what's in parallel and what's in series? Well, that's where the color coding comes in. It makes it so much easier. Realize that if any wire is touching, think of this as a conduit, a pipe that's full of natural gas because charges act like a gas, right? Well, anywhere that's touching here would have to have the same pressure throughout. And it's touching the negative terminal, so it's going to be blue. And anywhere up here that's touching throughout is going to have to be the high pressure red. So sort of like this. Now, since these are all equal resistances, the wire in between these two equal resistances must be exactly halfway between the pressures, which would be yellow. And so it makes it very easy to figure out which ones will be lit up and which ones don't light up. The ones that light up will have the pressure difference across them. R4 will not light up because it doesn't have a pressure difference. Further, the ones, since they all have the same resistance, the ones with the greater pressure difference across them will be the brighter ones with the greater flow. So R3 is going to be the brighter one. It's going to have no more flow through it compared to the branch over here with R2, R1 and R2. Let's look at another situation. The circuit on the left, this is kind of what we did with the dueling batteries. And we saw that the light bulbs didn't light up. So the question is, over here on the right, it kind of looks very similar to that. Will those light bulbs light up or not? At first, it's not really evident what would happen because it does look similar. But as soon as you color code it, it becomes so much more obvious of what happens. Notice up here, everywhere touching the positive terminals red, same thing on this side, everywhere is touching the positive terminals red. That means there's no pressure difference across the light bulb, so it doesn't light up. Down here, everywhere touching this is a low pressure, everywhere down here is low pressure. There's no pressure difference across it, so it doesn't light up. Let's contrast that to the circuit on the right-hand side. Everywhere on the top is red, because that's a high pressure touching the positive terminal. Everywhere on the bottom is blue, because it's touching the negative terminal, same pressure throughout. And across this branch here, since they're equal resistances, they would have the same, they would have half the pressure in between them, so that would be yellow. And so there is a pressure difference across this light bulb. In fact, it's the same amount of pressure differences across the bottom light bulb. And so they do light up. So it's not the same circuit. Well, what about more complicated ones like this? Can this help too, the color coding? Well, let's try it. So everywhere touching the positive terminal is going to be red. Everywhere touching the negative terminal is going to be blue. But the question is, what is this color over here? I don't know what that color is. It kind of depends upon the resistances. But what is something that I know is everywhere that touches it is the same color. So I'll just call it color X. And then up here, I don't know what color that is, but everywhere it's touching is like color Y. So realize what I now know. It's going from blue to some color X. So that means 14 and 16 must be in parallel, okay? And then whatever that's equal to, let's say that's some value, I'm just gonna make it up, it has to be less than 14. Let's say it's 13 ohms. That's gonna have a pressure difference across it. And then the 48 would go from color X to color Y. That has a pressure difference across it. That means that whatever, let's say 13 ohms, is now in series with the 48 ohms. Up here, the 28 and the 2 have the same pressure across it. 28 goes from red to yellow, or red to Y, and the 2 goes from red to Y as well. So those two are in parallel. So yes, this color coding still helps us even if we don't know the colors. All right, so what about situations like this? Well, if we were to color code this, notice that these two circuits over here, B1 and B2, the two light bulbs have the same pressure difference across it, but they don't have the same flow. That's because they have different amounts of resistance. If there's less flow in B2, that tells you that B2 must be more resistant than B1 to this flow because it has the same pressure across it. It must be a lot harder to get the flow to go through. In fact, you can see that it's 3 times harder. That means the resistance is 3 times bigger than B1. And so you can say that B1 is, let's say, 1 ohm, and then you know that B2 is 3 ohms. And so you could figure out an equivalent resistance of that combined circuit in different various forms. For instance, over here, we're forming this very complicated circuit. And I know this is blue on the bottom and it's red on top. I do not know what the colors C and A are. In fact, they would probably be different. I don't know what they are, but it's some color C and it's some color A. I can see that in this middle branch here, B and 2 and B1 are in series with one another. And on the far branch over here, B1 and B2 are in series with one another. And so I can figure out the resistance of those two. And those two branches then are in parallel with one another because they have the same pressure across them. It goes from red to blue. So it still helps me figure out what the resistance would be too. What about with capacitors? Would it help with capacitors? I don't know. Let's give it a try. So let's color code this. Let's say on the left, A is attached to the positive terminal of the battery and B is attached to the negative terminal of the battery. Everywhere on this wire would be red touching A, and everywhere on the wire touching B would be blue. Now, true, I do not know what this color in between the 5.7 microfarad and the 5 microfarad is. I don't know what that color is, but I know that they must be in series with one another because there's going to be blue to some color, and then from that color to red. So I know they must be in series. So I could go ahead and figure out what that series combination would be for capacitance. Then after I figure out what that is, realize that the 3.1, the 4.1, and whatever that number would be, we know if it's in series, it's going to be less, so it's going to be less than 5. So let's say it's 4. So 3.1, 4, and 4.1, they must be all in parallel because they all have the same pressure difference across it from red to blue, red to blue, red to blue. So yes, it does help. This is the strategy you really should be employing whenever you're doing internet homework or any type of problems like this. And lastly, of course, you'd need to know for resistors in series, you add up the resistances, and if they're in parallel, it's the sum of the reciprocals is equal to the reciprocal of the equivalent. And for capacitors, of course, if they're in parallel, it's the sum of the capacitances. And if they're in series, the reciprocal of the equivalent is equal to the sum of the reciprocals. Of course, you need to know that. But what's more important than that is that to figure out the resistance of any particular resistor, you take the resistivity times its length divided by its cross-sectional area. The bigger the length, more resistance. The bigger the area, less resistance. Capacitance, we found out that the bigger the plate area, the more capacitance, and the bigger the separation between the plates, because that's where the insulator is, the smaller the capacitance. So that's what you're going to need to know for your internet homework and for our test.